All right, continuing on with inflammation here, part of the non-specific immune response, we see that the whole process of inflammation, because it's not really a specific cell or a soluble protein, it's a whole bunch of cells and proteins working together to do inflammation. The goal is to bring in, again, nutrients and fighters and help to keep that injury in this area and not spread, then clean that up and repair. So we said this containment happens because we have fibroblasts that kind of set down and close this in fibers, and we brought in all these neutrophils and monocytes that became macrophages. And so we say here again, injured cells that start the whole inflammatory process stimulate mast cells, basophils, phagocytes. These release a series of histamines, leukotrienes, and prostaglandins, and these two are classes of chemicals, right? And so histamines increase flow and permeability, right? So we're thinking why the redness, heat, swelling, right? And pain. Leukotrienes, cause chemotaxis, so they call other cells in. They increase the leakiness of blood vessels so that cells can leave it. Prostaglandins are increasing flow, and they will result in the pain, which is why, again, we take anti-inflammatories. We're usually targeting the prostaglandins. So vasodilation increases flow, responsible heat and redness. Permeability leads to swelling and clotting factors released. And recruiting phagocytes to eat and clean up all this damage. Right? That's the 12 o'clock chime. We are here at the specific, right? The adaptive immune response. And we want to look at T cells and B cells separately, but know that they together comprise this adaptive, this response that changes through your life and changes as you change. It changes with your encounters. So I say, well, innate can slow the growth of invaders. It cannot completely control the invasion because it doesn't really know what the problem specifically was. It can recognize patterns, as we talked about previously on bacteria, but it really, again, isn't sure what the actual cell and the clones that come from those cells are that we need to respond to. So this response is resistant to particular pathogens, again, the snipers, a variety of different pathogens, because these have receptors, and up to 100 trillion different receptors can be available in the body, not per cell, by the way. All right. These receptors are for the antigens that the pathogens have. So again, we said the antigens are the identifiers, and we need to find that specifically. And so the term antigen actually means antibody generator, though again, T cells don't make antibodies. So the antigens themselves, again, are molecules on the surface of these invaders that will cause an immune response. All right. So the primary adaptive response, so your first exposure to this pathogen, is generally not going to go well for you. You're probably going to get sick, right? So the primary adaptive response, so the very first time you encounter something, let's take chickenpox, because most people, it's a prevalent virus in this country, and most people in listening to this have probably had chickenpox or known somebody with chickenpox, okay? And the first time you encountered chickenpox at school or work or whatever, you got sick, all right? Okay? And I said this is because your adaptive response is not ready, all right? We said this works slower. Your innate is active, but it cannot identify the pathogen well. That's why you got sick. So this is a great demonstration of the limits of the non-specific. All right? Secondary. So the second time you came across this virus, all right? So, or any pathogen, if you had that first encounter, it's the second time you encountered it. So again, commonly the evidence suggests that anyone who has had chickenpox once will not get chickenpox or have chickenpox again. There are other things that can surface later in life, but not chickenpox, all right? And the reason that you're not going to get it again is not because you do not encounter that virus again. If you encountered it once, the likelihood is you're going to see it again, all right? But the second time, you're ready, all right? So I say it's faster, it's stronger, right? So a secondary, right, adaptive response, or a secondary immune response, is when you're re-exposed and you know this. And so this is going to come down to really memory in this event. All right? I said, why did you not even know you'd been exposed again? Immunological memory. So we are only as good as our memories. Right? I say something else. So along with these different receptors with specific binding to antigens, this is the ability to remember, right? That this was a problem. I encountered it and it was a problem. And this, okay, we say again, you know, what else do we need for the adaptive immune response to work? Is we need to be able to know self from non-self. So we have brilliant memory that makes us very good at the adaptive immune response and not getting sick again, and the ability to know that this cell does not belong in the body while this cell does. That's what I mean by know thyself. So as B and T cells both grow up, again, we started off with talking about the T cells, but both of these cells have memory and both of these cells have this ability we're going to talk about. There are mechanisms that help them not, right, to keep them from saying or identifying one of your own cells as the problem. Okay, so when you identify one of your cells that belongs to you as a problem or potential pathogen, then you develop autoimmunity, and that's never good. So for the most part, I'm guessing that everyone in this room, or most of you, do not have autoimmunity, and therefore this, what we're going to talk about, is functioning well. And this, that we're going to talk about, prevents your B and T cells from identifying your self-antigens. So just like we mentioned in the blood chapter, all the cells of your body have their own antigens. So if your B and T cells, you have an antigen receptor to your antigens, you have a problem. All right? So this T cell, looking at that, again, T cell specifically, but reminding you again that B and T cells are controlling the adaptive response. T cells have a direct control and even can control the B cells. So we're going to look at T cell mediated immune response here. Right? How to attack is often through a T cell, and so we need to look at the types of T cells. Recognizing an antigen is the most important thing, right? You have to know that this is a problem. So here we see a cell membrane, right? And here we see a receptor, right? So the receptor has these different chemical areas or regions on them, okay? So don't be lost in the simple cartoon. It's just this is representing a receptor in a cell membrane. So the antigen binding is done through the variable region because we want this to vary from T cell to T cell to T cell to T cell, because the antigens vary from pathogen to pathogen to pathogen, and even within one pathogen, there are possibly hundreds of different antigens, right? And this is a unique amino acid sequence. So again, these receptors are proteins, the antibodies are proteins with variable regions, and the antigens themselves can often be proteins. I say each T cell produces one type of receptor and it recognizes one particular antigen. So that's what makes this a very special, right, immune response. The T and B cells have only one specific type of receptor, and that one specific type of receptor recognizes one specific antigen. And this, of course, is why I mentioned earlier you have to have many varieties of B and T cells. All right? So here in this cartoon, antigens, again, revisiting this, are large and complicated. So again, simple things are not going to end up causing much of a response, or repeat simple chemical things. So again, this is why polymers of plastics can be put into the body and don't elicit an immune response, because chemically they're very simple units or molecules that are just repeated over and over again, and so we never had an antigen receptor for that really simple thing. So I say proteins or carbohydrates can be antigens, and these interact with many different T cells to start an immune response. But what that T cell needs, of course, is this antigenic determinant. So you'll notice here on this T cell, they have 1, 2, 3 different T cells. I said lots of variety, and each of them has recognized a different part on this overall, right, protein, foreign protein that's in the body. So, and then a specific area on this protein is called the antigenic determinant. So I say, actually T cells do not recognize free-floating antigens, believe it or not. So only when the antigen is on the surface of an antigen-presenting cell. So this is a hypothetical situation that's not going to continue the response, but it shows, again, these T cells have this recognition. All right, so the T cell does require the assistance of an antigen-presenting cell, and this cell will also process it. So here we're looking again at a T cell with its specific antigen receptor right here, and we're saying this antigen processing will chop up the molecule. So some cell, and often macrophages end up being this, though, and they're showing one here hypothetically. This can be a variety of other cells, but not a lot. All right, not a lot of cells can be antigen presenting and processing cells. So antigen processing consists of chopping up the molecule on the antigen. So this cell, right, would actually pick up, right, a pathogen, and they're showing that here, and it would enter the body. It would fuse with the lysosome, and the lysosome, right, would then, and here we see another entry here where it's just picking up a pathogen, but fusing with the lysosome, whether it's a pathogen or a soluble protein, and basically chopping this up. Right, so the lysosome destroys the pathogen and chops up the pieces of this. Right, so antigen presenting, the pieces are displayed on the surface, the plasma membrane, associated with this self-antigen called MHC. So here's the MHC shown here. There are two classes, 1 and 2, and as I say here, MHC1 is found on all cells except red blood cells and is used with intracellular antigens, which is what this is, a virus. MHC2 is on these, what we call these professional antigen-presenting cells, which are macrophages, B cells, and dendritic cells. And these, right, MHC2, will be presented with these pathogens. So it's just showing you two different routes that they can take. Here they converge, and they are displayed here. And the displayed, right, MHC and a piece of the pathogen or soluble protein is here too. And the T cell comes along, and its receptor allows it to bind to this displayed, right, MHC and pathogen. So this works really well because, again, what we're doing is we're showing this T cell, this presenting cell, this is a problem, this piece, and MHC is not. Okay, so don't attack your self cells, go after these things. All right, so it says here, what happens next? Again, this reiterates that MHC class 1 is on many cells. They're not, right, it's not necessarily a phagocytic cell. It stimulates the T cells. Okay, class 2 is on a phagocytic cell and stimulates phagocytosis and presentation. Right, so we've got a couple different things going on because of this processing. All right, so macrophages, again, stimulate T cells. That's what's important here. And T cells then synthesize and secrete a lot of different cytokines that help phagocytosis occur. So we're leaving out a few things on this table. Again, don't worry about this table. This is not what the point is. It's just telling you about these molecules that are really self-antigens. So bring the antigens to the regional lymph nodes so that T cells can recognize them. So that's why, you know, these cells that move around, right, like the dendritic cells and the macrophages, can begin to show the T cells, here's the problem. Is this a problem? Right? Recognize them. Do something about them. Right? And the T cells then direct the rest of the immune response. All right? So this kind of complicated cartoon in 1 minute left is looking at how T cells develop and differentiate. And so this reminds us again, they mature in the thymus, and they are able to recognize self and non-self. And a mature T cell can either have this kind of protein on its surface or that, among others, right? These are basically telling them what their job is going to be. This is a job description. CD4 a helper, CD8 is killers or cytotoxic. And they bind to different components of your self-antigen. So this is important too for this cooperation. The important thing, though, that happens to a T cell as they develop and differentiate is that they can distinguish self, right, MHC, and non-self antigens. Because if they can't, if you look at this whole cartoon, which again is very good, but not really, we don't have to spend time on this in class. We're not worried about, you know, how they do this selection. We're just really trying to tell you that they can.